Okay, good morning, everyone. It's a little after 9 a.m., so we are going to get started. My name's Anna Zylik. I'm with ICF, and we are the vendor working on behalf of Eversource and Energize Connecticut to bring these Passive House trainings to all of you. So thanks for joining. This is the third workshop of our 4-part building science series. And these trainings are at no cost thanks to Eversource, a proud sponsor of Energize Connecticut. Also in partnership with Connecticut Passive House. Just a couple reminders, we do have one more of these building science trainings coming up on Friday, next Friday, April 16th. So make sure you're registered for that one. Also, these trainings are eligible for AIA and THEIS credits. Additionally, with this training that we are doing on behalf of Eversource Connecticut, we are also offering a 50% cost share reimbursement for professionals pursuing either THEIS or fee accreditation trainings. So that includes the cost of the trainings and the exam. And once you become certified, we'll work with you to process that 50% cost reimbursement. Our email address is down below here on the slide, so feel free to reach out if you do have any questions. You will also receive some follow-up emails after the workshop today that will include a survey, and we do appreciate any feedback that you can provide on your experience participating here today. And with that, I'll pass it over to Mike O'Donnell with Stephen Winter Associates, who will be taking over.
Great, thanks, Anna. Good morning, everyone. As Anna mentioned, my name is Mike O'Donnell with Stephen Winter, and we'll do just some administrative stuff here first, and then I'll get into the intro and get into the presentation. So sort of the general outline for today is everyone's going to be put on mute, but if you do have a question, please put it into the chat when they come up, and then at the end of each section we'll try to take some of those questions to get those answered, or if we don't get to them, we can follow up after via email. The webinar will be recorded and sent as long as with the slides too, so if you miss anything or want to rewatch or share it with someone, all this will be available. And the last piece here is we do have a couple polls throughout the presentation that we ask for some responses to. So you can respond at pollev.com, or you can respond via text message. Either or works. So just to get that set up now if you can, so when the polls pop up, you can respond accordingly. All right, so just a quick intro for myself. Again, Mike O'Donnell, I'm a principal building systems consultant with Stephen Winter Associates. I've been with the company 9 years, almost coming up on 10 years. Can't believe I'm actually saying that. So I have a background in energy management and started off with smaller single family home type projects. And then since moving to Stephen Winter Associates, been working on mid to larger high-rise type of multifamily projects. And I'm working on our Passive House team, leading a lot of the field inspections and testing and field verification items on the various Passive House projects that we're working on. Also on the line is Joanna Grab from our company. She's helping behind the scenes today. Any technical issues or anything which hopefully don't come up, but she's also helping, and we'll be fielding some of the questions at the end of each section. So Joanna is also on the line. Today's workshop is about HVAC and plumbing, also a little bit of electrical. So the MEP trades is what we'll be looking at today. So a quick blurb about Stephen Winter. We have 4 offices now. Our newest office is in Boston, but we have offices in Norwalk, DC, and New York, and offer the range of green building certifications, sustainability consulting, and accessibility consulting as well. I think Anna mentioned this too, but if you need AI credits, that's an option, and the presentation again will be sent out. So these are kind of overall learning objectives, and can kind of look at these a little bit more closer. So first part, we'll do our quick passive house basics. Hopefully people listening and know what passive house is, but if not, we'll kind of run through that very quickly, and then dive into ventilation and take our first break around 9:50. Then we'll do our second section on space conditioning, and then more on ventilation. You'll see why I can talk about ventilation probably for hours on end. And then we'll finish up with plumbing and electrical systems. So our first poll for today, we always like to just ask who's listening in so we can kind of understand and maybe tailor the presentation a little bit to a specific audience. Okay, let me give it a couple more seconds here to steady out. Okay, so numbers might jump, but good amount of architects, some engineers, some contractors, and consultants, and maybe a few owners and developers. So I think that's fairly similar to what we've had previously, but all right, we'll keep moving here. So our next poll, what is the one thing that you're hoping to learn about today? And if you use an underscore, you can link words together so it doesn't get split up when it posts on the screen here. Ventilation, yeah, it's I think one of the hardest things to get right. Efficiency. Best practices. Yeah, commissioning is an important piece of the puzzle as well. Constructability. Systems that work well for passive house, that's a good one. Okay, so we should be covering most of these things in some fashion today, which is good. So just a little bit of background, why are we here doing these presentations? We're definitely seeing more of a push for passive house projects, in Connecticut, in New York, in Massachusetts. So it's becoming the sort of next efficiency level to be hitting for projects, or project teams are interested or want to know about it, or maybe want to take it on. So we have seen the interest grow for passive house projects. As Anna mentioned before, there is are some incentives available for professional accreditation trainings. So that's again trying to help push people to get certified so they can understand what a lot of this stuff is about. And the benefits we'll kind of get into in a little bit, but we know that it results in lower energy use, healthier indoor air quality, and more consistent temperatures as a few examples. So today is workshop 3, HVAC and plumbing. We also have workshop 4 next week, which will be the last one. And we've had workshops 1 and 2, which if you missed, I'm sure there are slides or recordings or something available, so you can take a look at those. So passive house basics. Again, we'll try to go through this fairly quickly. Assuming most people know what passive house is, but if not, it is a building standard. It's currently the most rigorous energy efficiency certification available. It's performance-based, meaning you can pick and choose how you design your building to be within your energy budgets. There's attention to insulation and reduction of thermal bridges, which we looked at in the previous workshops, and an emphasis on balanced ventilation, which we'll cover today. So some of the goals: building durability. You're getting a very well-built building. Obviously, the energy cost reduction. You're getting better thermal comfort, better indoor air quality, and of course, the carbon emissions reductions from using less energy. So this is a simple example of a passive house, but we have our sort of pillars of passive house: the thermal insulation, thermal bridge free or really mitigated construction, where you're minimizing where you have bypasses of your insulation, solar control, air tightness, but balanced mechanical ventilation. So this is a sort of easy, simple example of a passive house. But with that, it's not only just for houses, it's for basically any building type. We have some large high rises, we have some townhomes. This is an office building where a section of it is going for passive house. So it's not only for houses, it can be applied to essentially any building type. This was actually a garment factory in Sri Lanka that we worked on, kind of a random one, but to show that it can be applied to essentially any building type. So another sort of key component covered more so in the previous sessions and will be looked at in workshop 4. It's the air tightness. So this is for the building envelope components to make sure your air barrier is very tight. But this is also important for plays into the sizing of mechanicals and also the effectiveness of ventilation systems. And the balanced ventilation heat recovery. So we have our exhaust from kitchens and baths and supply to bedrooms and living rooms. So that's the sort of quick rundown. Any questions or anything there, Joe?
No, but I know that the group has been chatting about the FIA self-report code, so I have updated it in the chat section, or you can shoot me a question.
Okay, thank you.
We had a number swap by accident, so.
There you go. All right, so we'll get into our first section here, ventilation systems. So ventilation is really a critical component of a passive house project. And we'll start looking at some examples and layouts and potential ways to do it. But first we'll kind of look at why balanced ventilation is important versus typically what you would see is an exhaust only system. where you're just pulling from a kitchen and a bath and you kind of call it a day. And this also is, it's pretty important for air quality. You're bringing in fresh outdoor filtered air and supplying it to the spaces that you're, would most commonly be in. And, with the levels of air tightness that you're achieving with Passive House, you can't really rely on your gaps and cracks in your walls to be your fresh air supply. So you really need to rely on the ventilation system to be bringing in the fresh air that you need. So with that, you are adding a piece of mechanical equipment that is going to be running 24/7. So you do have some operating costs there. And with that, you need to be picking pretty highly efficient equipment. So you're not just getting, any ERV that you could find and throwing it in there. And some other key ideas are compartmentalization between units. So that helps, box out each unit from the neighboring units. And also other, there's overlap with other programs potentially. So using low VOC and healthy materials when you're building also helps improve indoor air quality. So this is an example of an exhaust-only ventilation system. So it's shown in a smaller apartment building, but you're exhausting, say, from kitchens and baths. And, where does your fresh air makeup come from? You're not really sure, right? It's probably being pulled from, gaps and cracks in your exterior wall or around your window or from your neighbor's apartment or from the corridor. So it's a little unclear where your air is actually coming from. And these are some examples of, showing from a different project, but fiberglass bath that's essentially black and dirty. And what this is showing is that it's actually acting more like an air filter because air is moving through it and, being exhausted somewhere, right? So this is showing that the air movement is coming from kind of wherever it can come from if you're not providing a dedicated supply to these apartments. So there's two sort of main strategies that we've seen implemented. There's either a central ERV or several central ERVs where you have the roof, the unit on the roof, or it could be inside or on a setback roof or wherever, the mechanical engineer can find a spot to stick it. But you're bringing in the outside air and supplying it to the spaces, and then you're also exhausting the stale air. The other approach is individual ERVs. So this would be an ERV inside every apartment, which we have some examples a little bit later of some of the drawbacks to that. There is also an approach called a semi-central, which we didn't even really show because it's very hard to get it implemented, where you'd have one ERV per floor and it would be serving all of the apartments on the floor, but you have to kind of carve out extra mechanical space for that to have the unit and have it all the ductwork distribution. So we've never really seen that been implemented. It's really either the central system design or the individual ERV design. So the ERV, there's essentially two types. There's a wheel or a core, but they essentially are doing more or less the same thing in concept. And it's bringing the stale air from the inside, crossing it through this core and exhausting it to the outside, while the fresh air coming in on an ERV picks up some of that heat and moisture. And actually the moisture is this way, but this is the fresh air being supplied to the space. And it's a similar concept with the wheel versus the core. So just trying to get a general sense of how often do you see a balanced system on projects that you're involved with? Okay, about half often. That's pretty good actually, if it stays that way. But okay, so often and sometimes are actually pretty good. So that's interesting. It's I guess that's good to see, because normally the result is, we're seeing exhaust only systems and you're not really sure where your makeup air is coming from. So that is encouraging that often and sometimes are the leading answers there. Okay. So another consideration is an ERV versus an HRV, and the ERV transfers heat and moisture, whereas the HRV just does the heat. So we have a more extensive sort of look into this and the pros and cons in our blog here. It's a fairly in-depth analysis. But for what we're seeing mostly in our region, it's ERVs being used. So that's either a rooftop or in-unit ERV is the primary selection for the ventilation. So some other considerations of, where do we put the ERV and what space is required to house the ERV, but also the equipment, or sorry, the ductwork that's associated with it. So here we have, this is the same kind of floor plate, and if the example was we need to put the ERVs one per apartment, you would need to carve out, they're assuming 10 square feet of space to house it and to have, the room to run the exterior ducts to the outside, and then you're going to have to run ductwork, probably do soffits and things like that to get it around the apartment. Whereas in this case, you have to consider the amount of space that you need to run these central shafts that are going to be running up and down the building and then branching out to the various rooms. So here is, the branch to the bathroom, the branch to the kitchen, and then the supply to it. If this is, this is probably a studio, so it would only be one. But then there's a, 1 bedroom, 2 bedroom, you'd have more supplies to those living spaces. So again, a lot of research has been done here. There's no kind of easy answer, but pointing to our previous blog post about this and kind of considerations of individual versus central system. One other consideration I'll bring up, and again, we'll probably look at it again, but with individual ERVs in apartments, you are not going to have two penetrations through the wall for the supply, intake, and the exhaust, exterior hoods. And now that's, however many apartments you have times 2 of exterior wall penetrations that you have to now be worried about for air sealing and getting those sealed for the blower door test. So, versus a central system that, you might have 2 or maybe a couple, 4 or 5, just penetrations through the roof or something like that. So some just additional design considerations. So we do need the supply and exhaust to be balanced within 10% in terms of the flow rates. So usually what the engineer tries to do is obviously per apartment match the supply and exhaust. And then, he has some play in, say, cellar spaces or back of house spaces with some flow rates there. But this is really a passive house requirement. So they want the ERVs to be balanced. You do need to supply air to all living spaces. We are exhausting from kitchens and baths. We do need a pretty good efficiency on the units, and we don't want to be supplying air that's very cold. So this is part of the design, is that you're not supplying air that's too cold to apartment spaces. And some recommendations, you don't have to use a certified unit, but you're probably going to need to be meeting your modeling targets. So we have seen only, especially for central ERVs, we've only seen 1 or 2 brands that are commonly being used, whereas the in-unit ERVs, there's a little bit more of a wider selection. And then the fan power, you want to keep that in mind of how efficient your fan is per CFM that it's moving. So we'll look at a few buildings that we've worked on that have used central, and I think we have some individual systems as well. So this building is kind of skinny but fairly tall, but they were able to have one ERV up in the sort of mechanical bulkhead room, come down sort of all the units, which we'll see in the next slide. And they did use one of the PH certified units. That is the route that most projects go. And one of the considerations, at least for this project developer, was easier maintenance and access. So it's easier to go and change filters in one ERV than trying to get into all these apartments and do filter maintenance, or if things break, they have to get into the apartments to fix them. And so this is just a kind of cut through of the building showing the general design. So we have the ERV up here, it's coming down and supplying and exhausting from all of the apartments. And then they also have a ground floor retail space, which they provided an ERV there. So when the tenant, whoever leases that space, comes in, they can hook up to the ERV. Most projects probably wouldn't do that. They would say, all right, retail tenant, you supply your own equipment and do what you want. But this particular project, they felt that, to be sort of aligned with passive house, they were gonna, sort of force the tenant to be using an ERV in that space. A couple of other add-ons. So we had demand controlled ventilation. So there was a few spaces, I think in the cellar and the first floor, like a gym and a laundry room. So that's where, there's CO2 sensors, and when those rooms aren't occupied, the system turns down and reduces the ventilation rates to those spaces. And they also felt that they needed to add a cooling coil to help with some preconditioning and dehumidification. That it's not seen on every project. It's kind of, some projects do it and some don't, but this project decided to add that. So this is a different project. This is what we'll call 511. They had a little bit weird of a geometry. So it's this little, what we'll call a sliver building, and then the main sort of core building here. So this is that, and this is the sliver. There's a little hallway here connecting these floors. And so their strategy was to sort of break it up a little bit. They have one main ERV up on the roof, and that was coming down and serving that sort of core building section. And then on the sliver, they had, I think, two smaller units over there serving the sliver building, and then they had another ERV in the cellar that was doing the commercial space and some of these first floor amenity spaces. And they also added this TCV control. So, kids' playroom, library, gym, all those spaces would get reduced ventilation when they're not occupied by tenants. And so this is just a kind of the snip from the mechanical drawing showing that. So they have the sensor, and that's wired back to these dampers that would change position and modulate the airflow based on if people are in the space or not. A couple other things though. So like we mentioned, the building form, this one is very weird. It's this sort of small building connected to this larger building. So I know during the design stage, it was kind of tricky figuring out how to actually break this up. But like we said, they came up with the one main unit for here, the one in the cellar for the first floor, and then two little ones to be serving this sliver building. And so that, took a while, I think, to figure out, but they sorted that out. The second sort of obstacle, which we didn't end up having to face, which was good, is that on these sort of mid to high rise projects, the owners want to try to do a split temporary certificate of occupancy, so they can occupy the lower portion of the building, say, while the upper portion is still being finished. And with that, it makes the ventilation system balancing nearly impossible. So, up here, these units may still be having sheetrock installed or painting or whatever, and these ones down here are move-in ready. So you can't very easily or necessarily do the balancing and sort of commissioning of the ERV system, especially if they're painting and they have registers taped off or whatever the scenario is. So we really advise against this, but owners have their own goals, right? They are pushing to occupy the building as quickly as possible. I mean, in this case, it turned out that they were so close that it just made sense to finish these upper floors so they could do the whole system at once, that it kind of worked out. But this is a kind of ongoing consideration on projects, especially that if they're a little bit larger in size. This is one from a more low-rise project. This is a wood frames project that's in construction now. This one's in Mass, and they've sort of carved out these little areas where the ERV and the outdoor VRF units are going to sit, and not as large in scale. I think it's only maybe a 3-story building, but they're doing a sort of similar approach where they have the ERVs up on the roof and then the ductwork's coming down and going to all the various apartments and common areas of the building. So this sort of central approach can be used even on sort of smaller scale projects. And so just kind of showing a general ducting layout. This is from that first one we looked at, this 211 project. So they have their main sort of shafts clustered in the middle of the building here, and then had their different ducts running out to the apartments. So here they're exhausting from the kitchen and the bathroom, and then supplying to each bedroom and the living room. And this is kind of fairly common of how it would be done. You do need to supply to each of the bedrooms and living rooms. So at a minimum, you'd be providing the bathroom exhaust and kitchen exhaust anyway. So you are now having to add more ductwork to get these supplies to be getting the fresh air to the apartments. So the individual ventilation, an ERV per unit, that's where you have your little sort of ERV closet, and you have the ductwork running just in the apartment. There's the benefit from the side that, from the owner's perspective, right? This is on the tenant's electric meter. It's not using that much energy, but it's a cost that they don't have to incur. But from our experience, these are pretty difficult to get implemented correctly. A lot of times these closets are very, very tight. They don't give you much space to work with. You can see that there's not much room, and he still has to make some connections to these exterior ports. And it really depends on the installer of how experienced or not they are with this kind of system. We've seen some that are just absolutely and honestly just horrendous, and it's kind of made it a little bit difficult to advocate for this type of system. We try our best to train people and show them and call all this stuff out and do planning early, but you really need to work with the installer to be implementing this correctly. So individual, right, we have talked about a cramped ERV closet, not much space, difficulty in properly insulating and air sealing these connections. So these are going to be definitely cold spots, and you need your insulated duct to be coming to the exterior wall and fully sealed all the way around to prevent any potential condensation, which is difficult given that they have this in here, but how, it's so tight, how are they actually going to provide any sort of seal around there is pretty difficult. I mentioned previously the penetration, so now you do have 2 penetrations per apartment, which can add up quickly and come into play for the blower door test. Future maintenance, filter changes, so now you have to, in theory, get into all of these apartments to clean the filters or swap out filters, which may be a problem with tenant access. And there's a lot of ways to do this, but if you're using flex duct, you have to make sure it's sized properly. Make sure it's not jammed in there, but that's pretty difficult to do given that these closets are fairly tight. So you'd have to take these into consideration during the design of, are we actually giving them enough space to be properly installing the ductwork in such a tight space. So just some more examples, you have to basically seal the ductwork along the entire length. So from the sheet metal takeoff to the unit needs to be sealed. All this needs to be sealed. They have a zip tie, but you have to seal that joint. This is all the flex. Then all the connection here needs to be sealed and either taped or caulked to the wall to make sure that this remains vapor tight. The duct coming off the unit here needs to be sealed, all the seams. This mastic looks a little bit light, and I don't really know how this is intended to work here. I don't know how you're going to be pulling through 2 boxes. So, this was a particularly difficult install. I think this installer didn't have very much experience with this type of project and system. So we, essentially went to the level of writing out each step, from the exterior cap all the way to, getting to the unit, past the unit, getting into the kitchens and baths, to try to make it as explicitly clear as possible to the installers of how this needs to be installed for it to be set up to work properly and pull the flow rates that we need, but also reduce any of that risk of condensation on the cold exterior connections. So, projects still continue to do in-unit systems, but we just have seen that they have been a struggle to date to get them installed properly. So coming off of that, some more just general items for having a shot at your ventilation system to be working correctly. So we call out AeroSeal for all central systems, and AeroSeal is a blown-in duct sealant. It's an aerosolized, I guess almost like an Elmer's glue, they say, that catches on corners of the ducts that are not sealed and builds up and kind of seals it from the inside. So it's incredibly difficult, if not impossible, to get the levels of duct tightness that you need from just hand sealing. So, every single project that we're working on that is doing a central system, we just have the engineer write AeroSeal into the spec from the beginning, just so it's clear that the level of tightness is called out and it needs to be achieved. The constant airflow regulators, car dampers, so these are sort of this little device that has a flap, almost like an airplane wing, and it reacts to the constantly changing pressures in the building, and it's set for a certain CFM rate, but they are adjustable. So if for whatever reason you need to change it, you can during the commissioning and balancing process. So we really do push for these adjustable car dampers to allow for some of that, tweaking or changing when you're doing the commissioning and balancing, and account for buffer on top of the design. So we, there's kind of an internal, how much buffer. We don't want to make it too high and, kind of strain our models, but you also don't want to have a project come back and, be hundreds of CFM over design, and now that kind of throws them out of compliance. So I think we've been saying maybe around 5%, assuming, the flow rates will be 5% higher. The extreme case would probably be 10%, but you wouldn't want to let the project team know that. AeroSeal, the typical AeroSeal spec for duct leakage, there's two different specs, but one of them is just the percentage, and it's 3% of leakage. So that's pretty tight. And so, there's all kind of play in these numbers, but we have been accounting for some additional flows beyond the design, for just, there's going to be probably some air leakage somewhere in the system. It's a couple of project photos. So this is the ERV for that, the 211 project for the retail space that they're providing for the tenant, whoever moves in. So you can't, it's kind of cut out here, but there's the two kind of holes in the wall that are blocked off. So they can run the supply and exhaust ductwork to through this wall and then into the retail space. And again, we're seeing a lot of, one of two manufacturers commonly used for central systems. This is also from the 211 project on the roof. So their ERV is in this mechanical space up here, and this is intake and exhaust, or vice versa, one or the other. You can climb up this ladder and you can get up in there. So this is their approach to the ERV. They actually kept it inside. This is the ERV from 511, the roof one. So this is up on the roof, and you have your supply and exhausts running off the unit there. This was before they insulated, but yeah, this is it's kind of deceiving, but this is a pretty big unit when you're standing next to it. We've also seen projects use multiple smaller units. So this is from a project out in Far Rockaways, New York. And I think they had 5 or 7 of these kind of scattered throughout. So this is again, same brand, but they decided to break up the building a little bit differently. So this is their ERV up off the roof, and the ductwork going around and coming in. It's insulated. And then this is back to 211s. This is there's 2 intake and exhaust ports here. The ducts are insulated there on the inside until they get to the unit. And kind of similar, these just smaller multiple ERVs from the Far Rockaway project. And so part of our, sort of final verification is checking, the airflow rates on the controller, and seeing how these compare to the tab report and how they compare to the design. So these guys have a pretty nice little kind of iPad thing that plugs into the unit, and it shows you all of this information very easily. It also shows you the watts per CFM, efficiency. There's a whole bunch of menus that you can go through and get data. So this is a way for us to kind of confirm what the balancer and the mechanical contractor have done in terms of getting the unit up and running, and seeing if these numbers are within 10% of each other and how they again compare to the design. And so yeah, this is just kind of looking inside, and the filters, these come with the filters from the manufacturer, but part of the maintenance schedule is making sure that these filters are cleaned or changed on schedule. So if not, this unit's gonna have to be working much harder to be moving the same amount of air. And this is also, you can see the wheel here on this design. It's kind of not the best shot of it, but you can kind of see it there a little bit. So with that, we also do have some filter requirements. This kind of MERV 13 is commonly seen for the central. I think the in units might be a MERV 8, but I'd have to double check on that. Might be a 13, I'm not sure. I'd have to confirm that. But another sort of requirement you have to keep aware of is if you're doing FIAS, FIAS also does want a MERV 3 or washable filter at the kitchen exhaust register. So that's something to take into account. We've seen people just buy these sort of large sheets of this washable filter and cut them into the sizes and put them behind their registers. And then FIAS also does call out their register to be at least 6 feet away from this from the stove. So this is something again to try to catch during the shop drawings and also during the rough-in of the ductwork to make sure this is actually being met. It's a little bit too late to see it when everything's sheetrocked and say, oh, well, actually they landed the register right here. So, to change that at that point is kind of invasive. So these are some FIAS items to keep in mind. All right, so tolerances are pretty tight, especially for FIAS. They want to be at least seeing the minimums are being met. So, if a kitchen is supposed to be at 25 CFM and it's at 21, that's, kind of well below what it needs to be. So you want to be seeing minimums met, and, they could be a little bit higher, but they don't want it to be any lower. We also, during the tab process, ask for a traverse of the ductwork for these larger central systems, in addition to the readout from the manufacturer's software, so we can kind of see how they compare to each other. The wattage, that's pretty easy to get, especially from that little iPad readout. And the tab requirements, we are calling out third-party certified air balancing professionals, and we really do need to have a meeting with them of how they plan to do the tab and what, instruments they plan to use and, you know, what measurements they're planning to take. So this is really a crucial piece and can be a very challenging part of the project, is getting these ERVs up and running properly. So with that, you know, we had a project where these are all in-unit ERVs, and the tab report that came out showed everything being, you know, perfect, right? The design and actuals were like, you know, exactly the same. It wasn't even like a 25 and a 26 or a 15 and like a 14 or something. So that's a little suspect. And then, you know, we were doing our verification for FIAS, and you know, saw that these flow rates were sort of all over the place, but mostly low and not being met. So we looked at the controller for the ERV and saw that, you know, none of the factory settings were changed. So that is very suspicious, right? How can you have been doing balancing or trying to balance the system if you didn't adjust any of the fan speeds or you know, change the settings? So, you know, we were in the process of attempting to go and rebalance, or actually balance these registers to the rates they actually needed to be at. So this was not a certified third-party tab contractor. I think that kind of played into it. So we kind of have made that a pretty strict requirement now, and that it needs to be, you know, a person that really is kind of in the tab industry as a certified person. And also, you know, we really want to try to be there the same day that they're there to go around and check and see that we're on the same page of all the flow rates that we're getting. All right, last slide for this section, this demand controlled ventilation. So we have seen this designed into some projects, again, where we're reducing flow rates to areas that, you know, where there's low occupancy. But there's definitely some considerations, making sure the sensor that they install actually can read within the range of, you know, what's sort of reasonable. You also have to set the damper positions, and you know, this is really when our commissioning team kicks in and they're helping and they're doing their commissioning scope on the project. So you know, it does take some effort to get these DCV systems set up and working properly. And you know, it should be included in the tab report. So if that's missing, that, you know, makes you question, have they set it up? Do they know about it? You know, what's kind of going on there? So this does take some effort to get these, you know, actually operating correctly. All right, a little long there, but I think we can take a couple questions if any have come in, Joe.
Sure, I have a couple of rapid fire ones. Can you define tab?
Oh, sorry, yeah, testing, adjusting, and balancing. So that's when, after the system, you know, a ventilation system is started up and running, you know, it's a contractor that's third party that comes in and measures the airflow rates and makes adjustments and changes as needed to get them to be within the tolerances and the ranges that are designed on the shown on the mechanical drawings.
Gotcha. All right, another one is there were a lot of questions about ERV filters. How often do they need to be changed? And I know we've talked amongst our team members about access to filters. So are there any tricks to placing ERVs when they're not in a central location?
Yeah, so I think it kind of depends. the actual location. Like I think projects in the city actually get dirty quicker, because of just general, bus exhaust and pollution like that. I would say, I think the general timeline is every 6 months. It might be every 3 months, if you're in a very heavy polluting environment. I think it kind of depends. But for in-unit, it's kind of hard, even if you locate the unit closer, as long if the ERV is inside of an apartment, you're going to have access to that apartment. So whether it's closer to the front door or deeper in the apartment, I don't think it necessarily matters. I guess you could try to do a closet in the hallway, but that, now you're carving out more space, and I haven't really seen it done that way. So it's a constant sort of struggle of in-unit ERVs is being able to get into those, I'm talking about sort of rental projects, but to get into those to change those filters. Whereas the central system, the maintenance staff can have easy access and go and change those pretty easily.
All right, and we had several more questions, but I think this was another theme. Do we want moisture being introduced to the building in the winter via the ERV? Seems that it would want to evacuate as much moisture as possible to reduce like high humidity and possible mold.
Yeah, so that's sort of the quote con on the list of cons for the ERV selection in that article that I think Thomas from our team wrote that. So yeah, that is a consideration, but they do sort of assumptions and I think some modeling to see that it won't be a problem. So that is taken into account during that design analysis to make sure that we're not going to have these potential durability issues in the winter operation with the ERVs. Okay, I think we're gonna just take our first break here. So we'll come back in 10 minutes, 10:14, 10:15, and pick it up from there. All right, so we'll pick back up and move to our next section here. Space conditioning, duct sealing, and more on ventilation. So for heating and cooling, really the primary way we're seeing passive house projects being heated and cooled is with the use of heat pumps. So, and mostly air source heat pumps. So there are water source heat pumps and ground source heat pumps. We have seen one project with ground source, but it's really the sort of this air source heat pump that's the primary system. We have seen a couple projects try to use traditional baseboard boilers and heating systems, which we'll, I think, touch on later, but the large majority are using the heat pump technology. And so there's a couple different ways to do this, but you know, the most common is that you have several indoor units, which are then connected to an outdoor unit, and then you might have, you know, sort of banks of these outdoor units serving different indoor areas. So there's a lot of different ways that the layout can be implemented, but mostly it's multiple indoor units to a single outdoor unit, and then you could have multiples of that. We have seen a project that did what we'll call one-to-one, so each apartment had an indoor unit and its own outdoor unit, but that does lead to needing a lot of roof space to have all of those outdoor units. You have this sort of what we'll call a condenser farm up on the roof, and a lot of times you don't have the space for that, and it's not really commonly used on mid to larger size projects. So with that, there are different options for these systems. So the heat recovery option we think is pretty important. So this is you can have simultaneous heating and cooling. So different people in the building can choose their temperature and be hopefully comfortable accordingly. Whereas the other system is, you know, basically everyone's in heating mode or everyone's in cooling mode, which is not the most ideal, especially in terms of, you know, tenant preferences and comfort. And the actual units themselves, we have either the wall hung units, which we'll look at in a second, or ducted units, which it does require some additional ceiling space, but you can then say have one ducted unit that's supplying the air to the various rooms within that particular apartment. So it reduces the amount of, you know, indoor heads or units that you need per apartment. So with the wall ones, you probably need one per room, which can add up. So this is our sort of typical wall hung unit. You know, depends on how you look at it. Some people think it's ugly, some people don't mind it, but this is an option for, you know, implementing the heat pump system. But the sizing is pretty important. You know, the loads in the passive house buildings are pretty low. And so picking the unit size appropriately is pretty important. And, the manufacturers, I think, are now coming out with some of these smaller size units, but even still, they're for a while, I know it's been difficult to get units that are, small enough in capacity that they're not oversized for the space. So that is also something to look at during the design side. We bring this up, snow is a design consideration. So obviously all of these fins need to be open to the outside air and not blocked by anything for the unit to work properly. So, I mean, this is a little example from, a single family house, but it shows that, it's sort of up off the ground. It has its little roof here to keep the snow off of it. So this could be a problem if it's not taken into consideration. A lot of times, which we'll look at in the next picture here, these units are up on a roof and they're also up on some sort of support or steel kind of dunnage system. So even if there is snow, it won't block the the unit and obviously affect the operation of it. So here's some examples of these sort of large condenser banks. You can see that there's this steel rack, more or less, that there all these various condensers are sitting on, and then the refrigerant lines are coming down and serving various apartments. This is just another view of it up on a roof, and hard to see, but they are elevated somewhat. So, these fins shouldn't be blocked when you have a snowstorm that could potentially be a problem. And so we have those units typically up on a roof or in a setback roof, or if it's a lower rise project, maybe in a backyard or somewhere, or even they might stick them up on a roof too. And you have all of the refrigerant lines then running down, across the roof down into the building. So this is sort of a big cluster of refrigerant lines. And this was before they had installed it, but there's, you want to not only insulate the lines, but also add a protective coating. So what we've seen used is just a pretty simple PVC kind of jacketing that goes over it. And it's really to protect it from the sun and the UV degradation that can happen over time to this insulation. It is a code requirement too, so we've been making sure that we push for that, because a lot of times if you look at an older AC system, you can and the insulation outside, you can see it's all sort of crumbly and falling apart. So we do want to insulate these lines, but also protect them from the sun where if they're exposed on the exterior. So keeping on the topic of insulation for these line sets, a lot of times the pre-insulated line sets coming from manufacturers don't have enough insulation on them. So this was from a project not too long ago where you can also, at least I can kind of tell when you look at it, it's not thick enough, but this is 1/2 inch insulation, whereas on this project, the engineer was calling out 1.5 inches. More commonly, it's typically about 1 inch on the refrigerant line insulation, but it's something to be aware of. That the typical go by pre-insulated line sets, they probably are not going to have the right thickness of insulation. So that is something to check with manufacturers to see if they can provide it, or if you have to buy them separately and do the insulation on site. And so this is from a project showing that, you know, they're running a lot of these lines in a corridor wall. And then you can see here you have, you know, it's not, you know, not showing the connection, but these are then running down the corridor and branching off into each apartment, you know, for the unit that it's going to be serving. And these are all insulated. I think this particular project they used, they ran all of the copper piping first, and then did the leakage tests to make sure that they weren't losing any pressure in the lines, and then went back and insulated them. I think they only left the joints open so they could insulate most of the pipe, and even through the floor and do the fire stopping, and just kind of leave any of the joints open. So if there was a leak, they could be able to find it. So yeah, this is, again, the sort of a better view of the ceiling. You can see that they're all sort of running in this fairly big gang, but then branching either into apartments or, you know, going back up to the riser. So it's just you have to allow for the space and, you know, the pipe plus the insulation, and make sure you have enough, you know, space in your ceiling to accommodate all this stuff, in addition to whatever else might be running up there. And so the sort of best practice on installing this is to do the leak testing with the walls obviously still open, and the insulation off, at least the joints. You know, I think this project might have gotten a little ahead of themselves, and, you know, the sheetrocker was really flying, and some of these areas got closed up, and then, you know, they found out that they did have a leak, so then they had to go back and kind of bust open walls and open it up to see and find where these leaks were. So I think they learned on that one, but most projects, what they choose to do is leave this all open, do their testing to make sure that there's no leaks, and then finish up and close it up with sheetrock. So they might have, you know, maybe they'll do sheetrock on one side, you know, if they have at least some space to get to the connection, but that might be a strategy too. So you can have some sheetrock done, but then wait until all of this checks out before closing it behind the walls. And so this is just showing kind of the before the installation. So you can see that there's a kind of big cluster of all these pipes, and you can see that here they have some offset. So there's all these different connections and joints that potentially could be areas, unfortunately, for leaks. So, you know, I think this area they probably, I would imagine, left sort of wide open, and maybe put no insulation at all until they made sure that they weren't having any problems with the lines holding. And so then all of those lines that, you know, sort of run into the apartments, feed into the air handlers. And most commonly what we see if you're doing a ducted system design, there's usually typically one unit per apartment that's ducted to the various rooms. Sometimes if it's a weird layout, you know, or a larger layout, you know, a 3-bedroom or something, maybe you have 2 units, maybe you have some ducted and some, you know, one wall hung unit and some other, you know, 4 bedroom or something like that. So there are different sort of nuances, but the majority are, you know, as much as they can have one unit in the apartment, and that gets ducted to all of the rooms within that apartment. So kind of getting into some commissioning items, they have, you know, the tags of the units is pretty important. You know, a lot of times you have these sort of large clusters of condensers up on a roof, and you know, it's can be pretty difficult to know what's serving what space. So you can see this one, it was marked as the electrical closet, and then it was they actually, oh yeah, this is the telecom room, so they just like crossed it out. Normally these should have sort of permanent labels attached. You know, I think just for the time being, they were doing Sharpies so they could at least keep track of what unit is serving where. But yeah, that's obviously important from a commissioning perspective, but also an operations you know, perspective of which unit is serving what space. So some of the wiring stuff, this one has the, you know, the issue is the wiring is crossed, you know, so make sure that it's obviously serving the correct unit. This note is about temperature, you know, the thermostat and what it's basing the temperature on. So, you know, there's the option of return air temperature versus the measured on the thermostat. Again, a commissioning item that would be called out by, you know, our commissioning team. And just making sure that the thermostats are reading fairly close or properly. You know, this one seemed to be a little bit off. So there are items that definitely come up during the commissioning process to make sure these units are up and running the right way. And if you're doing that strategy of, you know, one unit per apartment and ducting it, it is, you know, obviously important to have your duct sealed properly. So you're getting that airflow you need to each of the rooms. Most projects are using just traditional mastic, you know, paint on. This project actually chose to use this mastic tape, which is pretty interesting. So it's like a foil face tape, but it has mastic embedded on the back of it. Really the key connections are the top, all the top joints. Typically these ducts are very close or tight to the ceiling. And you know, there's really not much space to get in there to do any sealing after it's kind of been pushed up there. So planning how you're going to get those top seams sealed. Some contractors try to lay out as much duct as they can on the floor and seal it as best they can down there and then put it up. Or, you know, you kind of angle it. Yeah, it takes a couple of people, but you have it held down and you angle it down and get the sealant on the top before you're pushing it tight up against the ceiling. So there are definitely ways to do it. It just takes a little bit of thinking ahead and planning, because that could be a definitely weak spot if all the ductwork just gets installed and then you come back and try to seal it. You know, you can see sort of telltale signs when there's mastic painted on the ceiling in the corners. You can tell that they're just trying to get it in there the best they can, but they probably missed that top seam. Also, I don't know if the unit is in view here, it might be further down, but the, you know, connection of the duct to the actual air handling unit is pretty important to get that sealed. That can be a leaky area. And then also the the return side, making sure that that's sealed to the unit as well. So just a sort of general question, what are some negative consequences of not sealing your ducts the right way and for apartments or common spaces? Yeah, inefficiency, you're not going to be pushing the air where you actually want it to go. Yeah, I think it's comfort issues, right? So again, that say it's heating, the heated air is being pushed into the space, but maybe not necessarily directly into the rooms or areas that you're intending it to get to. For temperature control, yeah. Yeah, also balancing, I think, so I saw it's definitely going to be much harder to get the airflows you're intending in different rooms if you have leaks or disconnects in the ducts. So staying with duct sealing, it's obviously critical for heating and cooling ducts and ERV systems to get the flow rates that we're calling out and designing to. FEIS does require in-unit duct testing of heating and cooling systems, and this was actually from a project where they were using a ground source heat pump system, but it was similar in that they had their cabinet and they had the ducts coming off the top and serving the different rooms in the apartment. And we actually found that the ductwork itself, when we tested a sample of just the ducts, they were actually pretty good. What was most leaky was the actual kind of cabinet or box that was coming from the manufacturer. So obviously they weren't thrilled about it, but they had to, the GC had to come up with a way to seal, the box itself. So it was a combination of, mastic on extra sort of knockout panels and areas that weren't going to be used, some of these little like screw heads, some taping, metal tape around the panels. There's, 2 pipes coming in, supply and return. They use some rubber gaskets around those pipes. So this is definitely a consideration if you're doing FEIS and you have ducted units, knowing that you're going to have to do duct leakage testing, and then taking into account, assuming that the equipment may not be totally airtight. We have had I don't want to say better success, but not as much, observable leakage through the split system units, which are more common. But these particular heat pump units used in the ground source system, this box was very leaky. So we actually kind of pre-tested this and troubleshoot with the GC of all areas that would need to be sealed. So what they did is they kind of lined these up and did all this sort of pre-sealing work before the units were placed in their kind of tight closets here, and then attached the traditional ductwork to it from there. So something that normally it's a ducted unit and it's traditional sheet metal. But we have seen this one system called a cool duct. used, which is pretty good, and it's, we have seen some good numbers with it. It's, pre-made, pre-insulated, and it's all kind of sealed from the start. So you do have to, make sure the layout is correct and you can actually fit it based on, the other stuff that's in the ceiling. So that can be some coordination there that needs to happen. But this is something that we've seen that works pretty well. And this is us just doing a little test of that ductwork. And I think the unit is installed as well, the air handler, and then we just probably taped off the return there, and got some numbers on that. I think most of the leakage was actually coming from where this duct connected to the unit itself, not through the system. So we haven't seen it too much, maybe one project, but we thought it was pretty interesting. And then, more traditional ductwork is commonly seen. But again, it's those same concerns of making sure that they have the space to be able to seal the top seams and really get in there to make sure that those areas are addressed. Otherwise, you can see how tight the ceiling is, and there's really no way you're going to be able to get a brush or anything in there to try to seal those. And so we have just a couple of videos also thrown in today. This is us doing a sort of a traditional duct leakage test with our duct blaster. And it's not a requirement for Passive House. It is a requirement for some other programs, but we have done it on a few projects to show the contractor how leaky their ductwork is or isn't, and then also we can use some fog to visually show them where leaks are happening. We actually had a project, I think last week, where they had a more sort of high-powered fan than we had, and they hooked it up and they put some different smoke bombs into the system so they could visually see where they were still coming up short and seal some of those larger areas before they were doing the aero seal. So just kind of skip ahead here. Essentially, we're just hooking up to the duct. It's kind of stubbing through the floor here on this particular project. And then we have our fan and our gauge to get an airflow reading to see how leaky the duct is. Again, we don't normally do this because we are relying heavily on the aero seal and the basic level sealing that's going to come along the way. But if we have a feeling that a project may not be on track, we can come out and do this to evaluate how close they are, far they are, on meeting the tightness levels for the ventilation systems. For the heating and cooling stuff, especially if it's VSVR, doing those tests for that ductwork. And so part of our, hands-on demo, this class was supposed to be, in a classroom, but obviously with the current situation, we had to do some sort of mock-ups, examples. So this is our little sample duct riser. We have a branch coming out here and, another branch kind of coming down here. And this is doing an initial leakage test on that, similar to how we did it on the riser. We have a sort of different device here, which we're using that has a lower measuring range. And so again, we hook it up, we're blowing air into the system, and we're getting a readout from the manometer, but also it's hooked up to the computer. to show us what the air leakage is. And this is, nothing is sealed. We have it just kind of roughed together. There's some gaps here at these joints, so it's pretty rough. And with that, we were only going to 50 pascals for reference. No seam sealed. We're at 45, almost 46 CFM. And so that's pretty leaky, obviously. And this is not too uncommon for a just, roughed in, put together sheet metal operation. Obviously, they're going to be sealing the ductwork, but we just wanted to get an idea of how leaky, this would be just as is. So now, doing some of the sealing, we're doing some of the seams here, but we purposely put it, tight against the wall to show how hard it is, or, it's nearly impossible to get to that back seam, and this is fairly common. The ducts are roughed in, thrown against the wall, and kind of the sealing is thought about after. So now we're fast forwarding a little bit. So we got, maybe 3/4 of this seam here. We're trying to get around these collar like takeoffs. There's a seam in the duct here, seam to the back of the box. Kind of switching views here, so trying to, really get it in there the best we can. And doing these, takeoffs, and with an elbow, you have a lot of seams and areas for leakage, so we're trying to coat that whole thing. And we're doing the best we can, but we know it's not 100% because it's pinned against the wall. We'll see that we actually got some leakage through these pre-made boxes themselves, some of the seams in that. So you can get it obviously pretty good with hand sealing, but not really the best. And so this is, after, sorry, I'll rewind it. This is, we've sealed it, but now we're pumping in some fog. And so you can see that we are starting to see fog come from different areas. A lot of it, really is that back seam. Some of these back seams on the floor, it's a little bit faint, but there's some coming out of the box here. That's not totally sealed. Maybe some areas I didn't do such a great job on and didn't totally seal it, perfectly. So, what might visually look like, oh yeah, this looks pretty good, still can be fairly leaky. So that is also why, we do see the aerosol as being important to, really finish up the job and seal all these sort of final air leaks that are, really hard to get to by hand sealing. So yeah, it looked pretty decent, but then the whole basement was filled with fog, so still definitely some areas to work on. This is really focusing on these back seams, harping on it, but we do see this pretty commonly. The ducts are pinned tight against walls and ceilings, and then it's really difficult to get to those areas. Some coming out of the takeoff, even though we thought we sealed it pretty well. You can see here the seams in the box, actually some coming through there. So it's not as tight as I guess we thought it was, probably supposed to be. So with that, we did our sealing, knowing that we were simulating, we couldn't get those back seams. We got it down to 23.5, so pretty good. Roughly, I guess, half of what we had before, but still, not tight enough, right? So this is sort of illustrating why we really think we need to have this push for AeroSeal on projects to get the tightness that we need. So a little bit about AeroSeal. This is a sort of general setup of it, where you have the machine, which is essentially a fan. This is the sealant injection part of it, and this long sort of plastic shroud or tubing, and then that gets connected to the duct system. And the sealant is aerosolized and pushed into the ductwork, and it'll catch all of those back seams or little areas that are very hard to identify or get to with traditional mastic. So we do see it as being a key component of getting to the tightness that we need for these central ventilation systems. To really get to the tightness level that we need. So this is just a little view of the equipment. This is that's the fan. This is the shroud. This is the sealant injection component. And then you can kind of see it. It's sort of this mist, I guess, and it's hooked up to the duct system and is getting blown in. And it's controlled by a computer, and you can see the graph and how leaky it was to begin with, and how the sealant is sealing the system over time, and it gives you a final readout. So in addition to the AeroSeal, we also see these constant airflow regulators as being an important component of the ventilation system. So I mentioned these earlier. They come in different sizes and flow ranges, and again, we push for the adjustable ones. But they are very useful in getting us to the flow rates that we need to achieve. This is a little video of when we try to really crank it up. You can see it flutters and reacts to the changing pressures. So in your building, if you have wind or you have stack or different doors opening and closing, these essentially are reacting to these different changes to be pulling within the airflow range that they're indicated for. So not a totally dramatic video, but trying to show that it actually is regulating, and this little flap is changing based on different dynamics that are changing in the building. So you can see the some of the results here from a project. They're saying excessive leakage conditions, right? Multiple days, troubleshooting large holes or disconnects. The thing with the AeroSeal I probably should mention is that it can only seal up to a certain size. So you can't just have big holes or disconnects, obviously, in the ductwork. It's not going to work. So you need to have a decent install first, which is kind of what we showed in our video. We did a decent job, and we sealed it pretty okay with mastic. And then if we had AeroSeal, come in and do our basement projects, right, they would kind of get that last little bit. So it's important to have them the ductwork installed pretty well before having AeroSeal come and look at it and do their process. And you can see some of these reductions are pretty significant, from the initial to the final. So, if you have a large building and a lot of these, pin ducts or whatever the scenario is, a lot of that leakage can add up pretty quickly. And then these are some of the reports. So it shows, the initial leakage, and then over time, how it, the leakage is coming down. It tells you the leakage in the square inches of a hole would it be equivalent to, what they got it down to, and the percent reduction. So again, we really push this on every project that's doing a central system. But with that, we do want to have some caution. We don't want to do it too early. We had one project where the ducts stopped, here on the first floor, and they weren't continued down to the cellar yet. And then on the upper floor, they had some of these branch outs, but not the final locations where the, kitchens and baths were going to go, and the final registers and boxes. So for whatever reason, the project had some urgent push to do this. They wanted to do it, we got to get it done, blah, blah, blah. It doesn't necessarily really make sense to do it too early because you are going to miss, significant parts of the system. So we do want it installed after pretty much as much as the system as possible, if not all of it is in place. So it is getting the benefit of getting the sealant. This is just another example showing, they had this is where they had the duct to. They should, and this one kind of stops here. It's not going to, its final locations. This is, I think, this was like right before, a day or two before they were planning or told us that they were going to do it. We told them we didn't think they were ready. So it is something to definitely keep an eye on is, is the ductwork all there to get the greatest benefit of the sealing. Okay, I think, like I mentioned, I was gonna get back into ventilation. I think I have already, but just some more considerations, just because we do see ventilation as being the difficult part of the project to get kind of right, and it usually happens at the end when the system's turned on. So we have been spending a lot of time looking at ventilation items that have come up on some projects. This one isn't necessarily too hard to meet, making sure we have continuous R8 insulation on all the exterior ERV ducts, fully insulated and vapor tight. So for central system, there's different ways to do this. Some use like a rigid board and then put an exterior kind of facer on it. Others use, traditional fiberglass kind of wraps that are, would be acceptable for outdoor conditions. So there's a couple ways, or the in-unit ERVs, either using insulated flex ducts or using hard duct and then insulating on top of those. So not too hard for the central systems. For the in-unit systems, it's a little bit tougher to make sure you're getting that vapor tight connection, especially at those exterior ports. So pressure balancing. So this is, again, FIAS requirement is that you have either transfer grills, jump ducts, door undercuts. Sometimes, usually are not enough to get it there, but this is to have a return air pathway. So this is a requirement of FIAS when, you know, the ventilation system's running and the door is closed. You throw a hose under and see the pressure difference and make sure that there's enough kind of pathway for the air to get back. This is harder on when the ventilator or the heating cooling system is on because the flow rates are much higher. So projects have been putting in these return air pathways or transfer grills or a combination to be achieving this requirement, which is coming from Energy Star. And a couple others, just sort of unrelated, but just a concept we're throwing in here is any dampers in the building envelope are class 1 leakage rated. So normally you'll find these at, say, the top of a stairwell or an elevator shaft. These are tied to a fire alarm system. So we want to make sure that they're closed all the time, and obviously tied to the fire alarm so they don't open when they, you know, these essentially should hopefully never open, right? But you can see some of these are sort of roughed in, you know, maybe the controls aren't totally set up, but obviously if these are open and leaky, these are going to be a problem for the blower door testing. So it's a related item, but something to think about that's not necessarily tied to the ERV stuff, but it is going to have an impact on the blower door. Maybe touched on this a little bit. The ventilation commissioning is obviously important, and working with the tab contractor to make sure that the systems are up and running properly. Again, we have most projects have commissioning on them as well, in addition to passive house. So this is really making sure that the units are started up and, you know, supplying the flow rates, that they're within the 10%, that the watts per CFM is in check, and that the apartments are getting the rates that are intended. Trying to get through this a little bit quicker here, just keep on track. We have only seen one project with ground source heat pumps. Sort of a unique project. We don't see it very often, but it is a potential option. They did have all of these sort of loops and wells that they drilled down to have the geothermal system, and then they all kind of came into this location and then went up to a mechanical room up on the roof. So this is, you know, coming into this little room here, and then going up to the boiler room. But from a, you know, view in the apartments, it doesn't look that different. You know, this could have been used as a typical sort of heat pump system, but they chose to use geothermal. So it is an option. I wouldn't say it's very common, but we have seen it. So it is out there as a consideration. All right, I think, Joe, we might only do one or two questions to try to keep on time.
Sure. This is a good one. For sealing the cabinet of units, do you get any complaints from any manufacturers about voiding any warranties?
No, but we definitely talked to them about it, you know, and brought it to their attention that, you know, the GC reached out to them and said, hey, we have to pass this duct leakage test. And more so, they were, I guess, a little bit annoyed or angry at the manufacturer, saying, why are you selling all these cabinets that are leaky. So you do definitely need to start that conversation, but we didn't get, any pushback from them on sealing their cabinet. But obviously, if you're going to go down that route, you should talk to that manufacturer to just, see what they have to say about it.
Got it. Can you speak just briefly about retrofits? Do the same lessons apply?
Yeah, I mean, definitely from a, I guess I'll just stick to ventilation. Aerosol can be used in retrofit projects as well, but you have to make sure you don't have any of those big leaks. We definitely have some images from other presentations where, there's big disconnects or big blockages in duct systems that need to be addressed. So you probably have to use an inspection camera or something to try to see, if the aerosol is going to be an effective strategy. If you have any of those big disconnects or blockages, that's going to obviously be a more invasive process. And then two, you need access to the units to block off all the registers. So, it's definitely a little bit trickier to pull off, but, we do have definitely case studies and projects from the past that have done aerosol on existing buildings. All right, so we're gonna take just a 5-minute break now. Come back at 11:11 and we'll finish up from there. All right, so now we'll finish up here with plumbing, and then we'll also look at electrical as well. So for domestic hot water, essentially there's two approaches, right? Essential system, one or more big plants that serve many people, or decentralized water heater in many locations, you know, for example, one in each apartment or under each sink in, say, a commercial application. So just trying to get a sense of, you know, what people out there are seeing currently on, you know, maybe their projects. Okay, 50-50 for a second there. Okay, pretty close, 48-52, so kind of a split. So with that, I guess I'll just say that, you know, there are, again, the mid to high-res projects primarily go with the central systems, whereas some of our, say, townhome projects or, you know, smaller might have individual water heaters for each apartment unit. But, you know, once you start getting larger in size, really these, at least for now, central systems sort of dominate. So, you know, we have our kind of big central gas-fired water heaters that are then serving the building. We do want to pick, you know, pretty good equipment. So, you know, it's Energy Star, it's typically condensing types of units that are being selected for hot water. And so we'll kind of focus on the central recirculation systems. That is sort of the majority of, again, what we're seeing on the bigger scale projects. So, you know, with that, you do have a recirculation pump that's running and kind of, you know, looping this water around the building. So when anyone, you know, calls for hot water, it's comes pretty quickly. And so insulation on the piping obviously helps, but there are some things in the design side that can also be pretty beneficial to the hot water system. So this is a what we'll call typical supply. So you have this sort of express line coming down and then going, you know, have a crossover maybe on the first floor, and then, you know, feeding up to the apartments that are in those kind of stacked lines, and then coming back down, and then, you know, going back to the water heater plant. You know, usually they locate these up on the roof, and so sort of a optimized design is what we'll call the box design. So, you know, you send the water down, it distributes out, comes back up, and then they return piping sort of collected up here, on this top floor, and then returned back to the boiler room. So, again, on our sort of modeling and analysis side, some of the guys who work on that have done comparisons, and versus a traditional design versus this box design. But you're definitely saving on material costs, the pumping energy required, which translates to your DHW heating costs. You do need to be aware that, if you have all of this piping up here now, you have the ceiling space to accommodate that. But we have seen it implemented in a few projects now, and I don't think they had this design from the beginning, and then after bringing it up, they were able to change it in the design phase. So it was implemented or shown in the drawings without too much headache. And so an example of this is one of the Sendero Verde buildings. There's 3 different buildings here. This is one, this is another, and this is sort of the tall tower. And so they switched to this box design, and it saves a significant amount of recirculation piping, which is obviously cost savings on copper, which is pretty huge. And they also had some reductions, obviously, in DHW heating, and then the effects of pipe losses. So it had an impact on cooling as well. So this is something that is not necessarily field related, but is something that to think about from the beginning is, are there ways to maybe optimize the DHW layout and design for a central type of system. And so when it gets to installation, just checking that it's being implemented correctly. One of the key items is the pipe insulation. So making sure that we're getting the right sizes of insulation, it constantly, unfortunately, seems to be a struggle. It's based on the pipe diameter. So for these smaller pipes that are less than 1.5 inches, it's getting 1 inch. And then for pipes 1.5 inches and greater, it gets 1.5 inches. It always seems to be a learning curve with the insulator to get those sizes right. So we often have to work with the plumbing foreman or manager or someone to, obviously convey this concept, but have them have, some way of identifying pipes and noting to whoever's doing the insulation install to denote which pipe size gets which insulation. So it seems pretty minor, but it's unfortunate that it seems to be a common issue that comes up. So we try to talk about it early. We try to come up with ways that pipes can be marked so the right sizes are being used. We also do want to look at the insulation being continuous. So you can see that these are some big pipes running down a corridor, and they're using the insulation shields, and then the insulation is continuous there. Otherwise, if these aren't used and the pipe's just sitting on this hanger, these are all contact spots where there isn't insulation, which can actually add up pretty quickly of areas that aren't insulated. So we want it to be as continuous as possible. We know there are areas where it has to be, say, attached to a stud or something else. Just keep it as tight as you can. But for something like this, where there's really no reason why it can't be continuous, this is something to keep an eye on. So for our own use, there's this little kind of gauge. It's an easy way to just identify pipe sizes. And, it makes it very clear to the installer, what's the pipe size and what's the insulation. So this is one that I suspected was not right, by looking at the plumbing riser, and, asked for a little piece to be cut off. So I can see that it's 1.5 inches pipe diameter, but only 1 inch of insulation. So, there's 2 strategies there: kind of take it off and put it on the right size, or try to add an additional sort of 1/2 inch layer on top. So it seems minor. Pipe insulation should be straightforward. It kind of is an ongoing struggle to make sure the right sizes are going where they need to go. Some other things. So this one is, some good stuff and some bad stuff. They've, kind of made the holes big enough here that they can get the thickness of insulation through the wall to keep it continuous. But at the same time, these pipes are running very close to each other. Like, I probably couldn't even, fit my finger between the 2 pipes here for the spacing. So, they're probably not going to get the right thickness that they need. They're going to have to do something to try to keep it somewhat continuous at this spot. So, it's kind of an afterthought. They run all the pipes and then they insulate later, whereas you should really be thinking about, the pipe plus the insulation thickness is sort of the dimension that you need to be holding when you're doing these layouts. This is another example of, they were just starting, catching a pipe that was a little bit larger, that was hot water. This is all hot water with only 1 inch. So, crossing it out, telling them the size that they need, trying to catch it early before they get too far along in the process of the install. Okay, probably enough on pipe insulation there. So the hot water temperature set points, they're typically storing it in the tanks, usually around 140, somewhere in that range. And it gets mixed down, typically about 120 is kind of the delivery temperature that we're seeing. This is a mixing valve, so it mixes it down to a more reasonable temperature, so people aren't at risk of scalding or that kind of thing. So this is, again, some commissioning items, making sure that it's being stored at the right temperature and being delivered at an appropriate temperature, that you're not risking sending water that's too hot to the building. And the recirculation pumps, just making sure that it's the right size and it matches the submittal. The horsepower is, what it has been from the design. Making sure that some, different pump isn't installed that's much larger or something like that. So pretty straightforward for a verification item. In terms of, does this actually match what the submittal was intended to have installed? So that's kind of it on hot water from a verification side. Really making sure that the piping layout doesn't change significantly from the design, but you can have some obviously gains from changing the design to the box design. But with that, we do have a few projects I mentioned a little bit earlier that they are using hot water for heating as well. So, central plant sending hot water to baseboards and apartments. And then for cooling, they have these window AC panels underneath the windows that kind of close and are airtight and insulated. So it's an approach that's not very common, but we are seeing it from a developer on a few of their projects. So just I'll talk about it a little bit. You have your central boilers and heating plant that's sending, hot water to, in this case, baseboards in apartments. And similar to the other piping, we want it all insulated very well. We want the shields. So we are maintaining that continuous insulation. Obviously labels help, so you know what's supply and return. This is an older photo, but these were some heating risers that were sort of buried in a chase wall, and you can see that they've already started some sheetrock here, and these large sections of pipe weren't insulated yet. So the question was, how are these guys going to get in here to do this? Are they going to have to take this off? So keeping on the insulation theme of just making sure that everything that needs to get insulated is being insulated during the installation, and it's getting the right size. So the heating pipes actually need some thicker sizes than the hot water. So for other plumbing items, now it's just going to be sort of a little jump around of different topics, but we do want to insulate these roof drains. So these are potentially cold surfaces, right, that are in the coming into the building. So we are calling out insulation on these, so we don't have any potential problems there. So this is something to note and make sure that it's probably the plumber that's going to be doing this, or if they're subbing their insulation work out, to keep an eye on this as another item that needs to be insulated. Water flow rates, so making sure that any shower heads, toilets are matching. Obviously the design and submittals and the flow rates are what they are supposed to be. A lot of times we are working with other programs besides Passive House where you might need WaterSense labeled fixtures. So keeping that in mind and checking for that. And one of those other programs is Enterprise Green Communities. So there's some requirements for water metering to really be used as a leak detection strategy. So, they want to make sure that the toilet isn't running all the time. So this is sort of overlap. Again, this isn't necessarily Passive House, but it's, plumbing related and something to be looking for, that, if they're supposed to be installing meters, are the meters getting installed in the piping when that's all kind of going in at the rough-in phase. And so with the flow rates, you don't want to be obviously too high, using more water and using more hot water potentially, but you don't want to be, too low that you're, making tenants feel like, oh, I'm not getting any water. What did they, why did they put this aerator restrictor on there? So there are some code requirements, and then also some program requirements. Again, if it's WaterSense is required, but I think even like at least the New York code is calling out WaterSense for certain things. So this all kind of plays into the flow rates, but also the hot water usage potential of the building. Again, just jumping around to a whole bunch of plumbing topics, not an easy way to kind of string them together, but any pumps that you have, that if they're called out for being a certain efficiency, making sure that those are the ones that actually get installed and the sizes are the right size. Should be fairly straightforward as long as you're comparing against drawings or submittals. Making sure what's actually installed is meeting what was approved by the design team. And sort of our last kind of random one for plumbing is any sort of heat tracing. So if you have, piping that's just running in a garage or any other crawl space or something that might be outside the thermal envelope, it might be a cold location. Sometimes the engineers design it with heat trace. So this is a kind of electric cable, heated cable that goes on the pipe that would turn on to keep it from freezing in cold weather. And with that, there's different technologies, and one is ambient air sensing. So it just measures the air temperature and turns the heat trace on or off. Or there's this pipe wall sensing, which actually has a sensor on the pipe itself. And so really it should be this pipe wall sensing because, the pipe is insulated and it has the heat tape on it. But, if the outdoor air is cold, it might turn the system on when the pipe itself is not actually that cold and would need the heat trace to kick in. So we do check for that in the specs and then also during the submittals phase to make sure that the type of control is the right one, to not be turning on this heat trace system when it doesn't necessarily need to be turned on. So that's sort of the run through there on plumbing. And now we'll get to electrical and kind of finish up from here. So really the main things for electrical are obviously lighting and lighting selections. They have these lighting facts labels out now. So it's showing the watts, the lumens, that light output, the color temperatures, right? The efficacy. So we obviously want to be using pretty efficient lighting where we can, and have, we want to keep the wattages low, but we also want to provide adequate lighting. So we don't want to sacrifice, saving energy for, having it just a dimly lit kind of unsafe building. So there are some balances there. But, we are seeing a lot of projects using pretty much all LED fixtures or mostly LED fixtures, and then say, T5 and T8s in, back of house or cellar spaces or things like that. But more and more we are seeing, just all, full LED lighting packages. And, again, this is during the design, but, checking all the wattages and the quantities to make sure you're, evaluating what the usage is for all the lighting. And with that, we're, for a field verification, you're just essentially just checking model numbers and tags to make sure they match all of the design documents. But some LED fixtures, the label is sometimes, like in this example, it might be installed on the back side of this fixture, so you can't easily see it without, taking it off the wall, which we obviously don't want to do. Or, some of them may not have a clear label easily, on the front or something. It might not even be on the back. So Usually we try to ask the project team to keep some boxes, or if they get a big shipment of lighting, we can kind of verify it that way. Because we have run into issues where the LEDs are not easily sort of identifiable, at least from what we can see. So there's a strategy to keep track of it by, keeping some of the boxes or looking at the shipments as they arrive. So some typical layouts, right? We have our bathroom light, a corridor light. Again, seeing a lot more LED packages being used. These back of house spaces, they chose to use, I think this is all LEDs, and they also have the occupancy sensors. So you see occupancy sensors in a good amount of spaces. Definitely, storage rooms and, say a bike room and places like that. Some rooms that might be a safety concern, like a boiler room or electric meter room. Some owners don't want to put them in those spaces. Most projects are using it for corridor lighting. So it, say, turns off every other fixture, and then when it senses someone walking, it'll turn on all the fixtures. We also do see it in stairwells. So it usually dims the light down to a certain percentage, maybe down 30 to 30%, something like that. But then when someone's walking in a stairwell, it triggers on to the full brightness. So the sensors can either be built into the fixture, or they can be on the wall or ceiling mounted. There's a lot of different options there. So again, this is some of these boxes as an example. Being able to verify it this way, or some fixtures are clearly labeled. They even have the Energy Star tag and that kind of thing. So that is much more helpful for the verification side of things. So with sort of lighting selections, we do sort of caution about decorative lighting. It's usually pretty energy intensive, doesn't put off very much light, and can kind of creep up and have some impacts on the energy model. So, if you have sort of one big sort of fixture in the front of the building, maybe it can kind of stomach that and be okay. We have seen problems where, on, say, every floor, they want to have this cove lighting around the elevators, or cove lighting run down the entire corridor. A lot of that wattage can add up pretty quickly. So just something to keep in mind during the design of, a lot of sort of fancier buildings want to do, decorative lighting, these LED strips, various wall sconces and other things that, may not necessarily be contributing to actual effective lighting, more of like a sort of mood lighting. So something to note when the design is happening of these lighting layouts. Oops. And exterior lights, again, we're seeing a lot of LEDs, and most have a photocell built into them, so they would only turn on at night. Others are controlled by a time clock. And so really what we're looking to see is that these lights are off during the daytime, right? There's no reason for them to be on during the day, and that they have some sort of control to turn them on at night. that whether it's a photocell or a time clock. So getting into some of the controls, this is a pretty simple narrative for a I guess sort of a smaller multifamily building. The corridor, they want the ceiling mounted sensors, and they want lights off within 20 minutes. Same for these laundry room, bike room. These have some common space bathrooms, exterior lighting, garage. Some people like, it depends on the project, but if they have safety concerns, maybe they don't go totally off. They go to some sort of level of dimming. And so these are all just samples of how to have lighting controls to reduce the lights being on all the time. And so it can get kind of confusing of all of these different strategies, especially of what things are called out in codes. So I've seen a pretty good guide from Lutron. Lutron isn't the only manufacturer of lighting controls, but it did have a pretty good document here outlining, what kind of solutions can be used to achieve the intended lighting strategy. So, here they're showing if you want occupancy sensing, you want multi-level, you want daylight harvesting, it will kind of tell you which potential application or products can be used for that. Some projects don't need to be this involved. It can be just a sensor on the wall. That might be enough, but it can get complicated if your project wants to and is looking to go there. So if you want demand response, energy monitoring, all this stuff, there is that level of detail all the way down to just the simple sort of sensor on the wall here that we would kind of more commonly see, and that's probably easier, easy to install, implement, get it set up properly. So most projects do sort of opt for these just more simple sensors on the wall or built into the fixture. Just one sort of nuance in the terminology. So this is especially in the, at least in the New York code, that the vacancy sensor is where you manually push the switch to turn the light on, but then it automatically turns off when no one's no longer in the space. An occupancy sensor automatically turns on and auto turns off. So the occupancy sensor, you might get some false triggers, if someone's walking by and didn't necessarily enter the space, it might trigger it on even though it might not have been intended to. So that might be a benefit of having it set up as a vacancy sensor, where you actually have to push the button to turn the lights on. Sort of covered this before, but this bi-level lighting, especially in stairwells, all the stairwells are kind of at a lower light output, until someone's, it triggers to full light level when it's sensing someone walking in the stairs. And so you would design this to be achieving the code minimum lighting, but bring it up to a more reasonable level when space is actually being used. And normally we see that built into the fixture. So here's the fixture, and this is the sensor that's built right into the fixture. So sensor placement is kind of important too. You obviously don't want it to be, say right behind a door or something where when someone walks in and the sensor doesn't pick the person up, that can be a problem. So, hopefully the locations on the plans are sort of thought out of where these sensors are indicated, but also during the install, making sure that they're located in a way that they're not getting obstructed or sort of placed in a spot that doesn't necessarily pick up the movement. And so these are, some examples like I talked about false on. So when it picks up movement that it wasn't intended, or the false off is when it turns off when someone is actually still in the space. So some other things to keep an eye on when you're picking sensors and where they're going to be located. Daylight zones, so you don't see too much of this in multifamily, maybe, some areas on a ground floor space, but this would be where the lights that are closer to fenestration are controlled separately from, say this middle band or and then the interior area of lighting. So, this would dim or turn off lights in these zones here if, they're receiving enough daylight naturally that they don't need the lighting to turn on. So just another potential strategy. Might have it on a multifamily, but probably pretty rare. Not too common, but it is more applicable to more commercial type of projects. All right, so another quick poll. What issues have you seen with occupancy or vacancy sensors? So we do, push a lot of these on projects, but, they're not perfect. So just trying to hear, if people have seen any issues with these types of controls. Yeah, the locations, the false ons. Yeah, bathrooms can be a problem if you're in there and it turns off on you. Yeah, the calibration is adjusted to be sensitive enough, right, to pick up on someone's movement. So yeah, these are all kind of things to think about when you're picking sensors and the different technologies that are out there and the placement and how sensitive they are. So you don't want to put these in at the expense of, really annoying people. So there is some more that goes into it than just taking a sensor and putting it in there. There's some more design thought that needs to kind of go into it. Right. This is a small one, but just elevators. It is in the code that they do have efficient lighting. So this is not too hard to meet, 35 lumens per watt, but most likely you're going to see the elevator cab with LED lights. And then this one is pretty interesting. It's when the elevators stop and unoccupied, that the interior lights turn off. So, middle of the night when no one's really using the elevator, or middle of the day, or whatever the time period is, it's another strategy that can be implemented to, keep lights off that don't necessarily need to be on. Again, sort of jumping around, random thoughts. So for electric, the cold water boosting pumps in mid to high rise buildings, just making sure again that the sizing is what has been designed, and that is really matching what the modeling assumptions and the submittals are showing. And the sort of last topic here is pretty straightforward, but metering, that everyone's directly metered or sub-metered for their electricity. So that's pretty straightforward, just making sure we have all of our meter banks and showing, or seeing that everyone's going to be responsible for their own electric bill. Also should hopefully influence people's behavior, right? If they're paying the bill, then it is a little bit different than if it's all included with your rent. So with that, we just would like to ask your final thoughts and feedback from the presentation today. Good, bad, indifferent. We just kind of get a sense of what everyone thought of the presentation. Good overall, great videos. Thanks. That was kind of fun doing that in my colleague's basement. Details, yeah, we try to show some project specific stuff. Balance the importance of duct sealing, which is critical for many systems. Lots of info. Yeah, I could probably keep talking about ventilation. Fortunately or unfortunately for hours on end. All right, so I have a couple minutes left. I think we'll just kind of park it maybe on this one. For any couple of questions, Joe?
Sure. There were a couple of comments about lighting and just that we're seeing lighting daylight zones in offices and high-rise offices. Someone had a good point that ugly buildings aren't sustainable. They're more likely to be torn down or not maintained. So kind of looking to the existing strategies, like different kinds of controls is important. But I think there's one comment that really drives home the usability side. And I don't know if you've seen anything, especially in the New York City world, in terms of lighting controls for occupancy or vacancy sensors. How have people tackled being sitting at a desk and not really moving and having to kind of wave their hands back and forth so the sensor detects that they're in the space? Have you seen like a temporary override or like a longer term timer on those?
Yeah, so there's the two different technologies as well. I think I kind of skipped over that part, but the infrared, right, and the ultrasonic. So I haven't seen it though where you don't have to move, unfortunately. So probably do have to, wave your arm or do something to keep the lights from turning off on you. If you know you're going to be in there for a while, maybe you could, temporarily override it. But yeah, I think they've also seen that in our Connecticut office, right, Joe? Like, we have sensors in some of those offices, and they might turn off on people if they don't move. So I don't know if it's been totally, I want to say, solved, but yeah, it is definitely, it can be obviously annoying, with the sensor turning off on you, but you could probably set the delay for longer, or, it's kind of silly, but remember to, stretch or do something where you are actively making a movement to, trigger the sensor to sense that there is movement and keep the lights on.
Active design.
Yeah.
One other question that folks are asking about AeroSeal, what are the claims for like safety there for the components that are inside the AeroSeal material?
Yeah, so it's, again, they kind of compare it, I guess, in consistency to this Elmer's glue. It is a low VOC product. They have the data sheet on it. I don't know the exact VOC content offhand, but it does, we see it used on enterprise green communities projects, and it hasn't been an issue there. Again, with new construction, it's easier, right? They would do it, and then any of the remaining, I don't want to say particles, but I guess that's probably the best word for it, kind of get out of the building over time, probably before people move in. I do know for existing applications, they can set up these sort of big scrubbers that have air filters. So that helps with that concern of any of these particles being introduced to a space. But I know the material itself is a low VOC product. It's not, shouldn't be toxic to the system or tenants. So they obviously took that into consideration when formulating what the sealant was intended to be. All right, so I think we'll maybe park it there for today. We have one more workshop next week. So thanks everyone for listening in, and have a good Friday.